Happy Friday. Hope everyone is doing well. So, yesterday I sent an announcement regarding the class, or maybe I guess I'll wait for another 2-3 minutes because students are still joining. So we will be able to finish this chapter today, and I already extended your homework and quiz by a day. But for some reason, if you need extra time to understand the material, or if something not making sense, let me know. So your quiz is due on Monday now, and homework is due on Sunday. But if you think you need more time, I can move your homework assignment to Monday also, and quiz to Tuesday. Or if most of you want that way, then I can do it for the whole class. Just let me know by the end of this. How do you feel about the homework? And there are not very many questions in the homework. I think there are 23 or 24 questions. But this time you have to solve some of the problems. They are not just a multiple choice and pick the best conceptual choice. There will be questions on conditional and marginal distributions where you have to solve it manually by finding which conditional or which marginal we are working on. All right, let me see how many. 28 of you are here. By the way, Miss Minion will not be joining this class today. So if you're writing something on the chat, she's not here. She will not be able to answer. But if you have a question for me, then please ask me and I'll go over that question. So good morning again. Happy Friday. Yesterday I sent an announcement about how our class will be starting from Monday. And again, as we discussed and mentioned in my earlier classes, that starting from February 15th, we are moving to on-campus, and our classes will be in Sullivan Science Building. So yesterday, we got the information that the classes can be moved to the same way as you are working on until further notice. And I don't know whether that further notice will be after 2 weeks or 3 weeks. But again, next week we have test and we have review session. And it will be, and according to our old plan, we were planning to start the classes on February 15th on campus for the sessions and the exam. And again, the weather forecast was also not good for next week. And since it will be the first week of moving with from online to on-campus review exam, so we decided to keep on continuing the classes in the synchronous way like right now we have from last 4 weeks. But again, I don't know how long it will be. But as soon as I get the information, I'll let you know. It can be for 3 more weeks or 4 more weeks or for the rest of the semester. To be honest, I don't know at this point. But I think at least for 2 weeks, I know 2 weeks for sure we will have. But again, there is so much uncertainty. Vaccine, I don't know when all of us will get. And there are so many other things. So long story short, we will continue our classes the same way how we are doing it in next couple of weeks. And as soon as I get the information when to move, I will let you guys know. I will not tell you that, hey, today is Sunday night and tomorrow morning you will be on campus. So you'll get enough time to prepare. And regarding the test, since next week we will be online, so I'm planning to provide you an online test. And again, the exam window or exam time will be 15 minutes during your class time on next Friday from 11 to 11:50. But still the decision has not been made if the test will be on Launchpad or on Canvas. So I will let you guys know on Monday. But again, it will not be on campus. It will not be face to face. It will be during our class time. But again, on Canvas or Launchpad, I still did not get time to decide. But I'll let you guys know in your review session on Monday. And for exam, as I mentioned earlier, you can use a 3 by 5 inches cheat sheet where you can write all the formulas. Again, you will be tested on the knowledge of the concept, not memorizing the formulas. So as long as you understand that part, you'll be fine. And again, we will do review on Monday and Wednesday's class, and you will know how many questions, what is the format of the exam, time window. Again, as I mentioned, it will be during your class time. Maybe I'll open it like 10-15 minutes before and 10-15 minutes after, so that if you want to start 5-10 minutes early, or if you are late for the class, so that you will not miss that time frame. So this is one thing. Second thing, like we are going to finish this chapter today, the last topic. And as I mentioned, your homework is due on Sunday, which has already been extended because we did not cut to cover everything. Today's Friday. You will still have time until Saturday and Sunday. But I know this weekend, so many things are going on. So if at some point you guys feel, or by the end of the class, if you let me know, even if you write it in the chat, if you want the homework to be extended, then I can extend it by Monday. Like, it's not a big deal for me. My only part is like, you need to understand this concept. I don't want you to rush on this homework assignment. Take your time. When you understand all the concept, still you have 3 attempts. So you don't want to take all 3 attempts on the same day. You need to take one attempt, see what you miss, you go back, read that part, understand that, and then you do the second attempt. So you should have enough time. So if you think Monday is an ideal day instead of Sunday, I can do that, and then quiz on Tuesday. And we will have review on Monday also. So if at some point you have questions, you can ask on Monday's class also. And then once you're done with your homework and quiz, then Wednesday, actually you can ask all your questions. And I will go over some of your homework and quiz questions on Wednesday's class also. And then your exam will be on Friday. Third thing, Miss Minion is not joining our session today. So I will read all the messages after the class is over. So if you have any questions that need urgent attention, either you stay after the class or you can stop. All right. Any questions for me?
I have one quick question, if that's okay.
Yeah.
Are you the one that makes the decision about if we go back face to face or not?
No, I am not the only one. There are so many. Like we cannot take the decision by ourselves. It should come from the university, from your department, and there are so many other things involved.
Okay, thank you. I was just curious.
Yeah, if I am not the only person. Actually, I want face-to-face classes. That's why I opted for face-to-face. We have online option also. But again, when they give you the classes, they decide, and then we cannot. Like, it's not just your own decision. Then everybody will run their own way. Then, yeah. All right. So, any other questions? If not, let's talk about the last topic. So we talk about two-way table in the last class. And when we say two-way table, so we are talking about a table. And we know that we cannot make a table until we have a row and a column. So table, if you are making a table, table represent rows and columns. And then that table is called as two-way table. So we can read the results in 2 ways. One by reading the columns, and the second by just reading the rows. So when we talk about two-way table help us to understand the relationship between two categorical variables. And when we are talking about categorical variables are those variables that we use categories or groups to represent those variables. And when we talk about categorical variables, the graph that we use is either a pie chart or the bar graph. So when we say pie chart or bar graph, we cannot use both at all the times. Bar graph, you can use at any time to represent a categorical variable. But sometime you can use pie chart and sometime you cannot, depending upon what is the total percentage of all the categories that you're representing. If that percentage adds up to 100%, you can represent that categorical variable in the form of pie chart also, but otherwise it is bar graph. So that is one thing. Then we talk about marginal distribution. When we say marginal distribution, we are talking about a distribution where we work only with the margins of that two-way table. So where we are just using the margins to calculate, we are talking about marginal distribution. And what are margins? So when a two-way table is given to us, we create an extra row, an extra column to create the margins of this table. And what do we do in that? We do the row total and sum of column total, and then the grand total or the whole total. So when we are talking about marginal distribution, we just work with this over this or this over this. So either the row or sum of column divided with your number of observations or all the observations. So marginal distribution, we talk about the margins. So numerator always comes from the sum of either the column, so this, or sum of rows, and your denominator is always all the observations. And where you get all? Here, the grand total, the sum of rows and sum of columns. So that is marginal distribution. When we are talking about just the margins and doing the calculation, it talks about the row, or you can say it talks about this particular row column, this particular, but it does not tell us the relationship between two categorical variables, because we are talking about as a group as a whole. If we need to find the relationship between two categorical variables, we work with conditional distribution. And we did this in the last class, but again, I'm going over with this because you have questions in your homework and quiz on that. And in the exam, you will find questions as well. So when we say conditional distribution, the word has condition in it. So you do a distribution where some condition is given to you, and you use that condition to find the distribution or find the results, and then you can do the relationship, or you can measure the relationship between two categorical variables. So when we talk about conditional distribution, we go inside this, and this is we call a cell. So when we do marginal distribution, we work only with the outside part. But when we work with the conditional distribution, we go inside the cell, and my numerator comes from here, either from here or here or here, depending upon what I'm looking. And if I'm talking about this cell is a combination of these two. I do not get this number just by looking at the column or just by looking at the row. So the example that we did, female, almost no chance. If I'm talking about this number, and I think that number was 96 or 98. So if I'm saying, what is this 96 means? Just the number of females? No. Or just people have no chance, almost no chance? No. This 96 represent female who said in the survey that they have almost no chance. So it is a combination. So when we are talking about cell is a combination of row and column. Same thing if you're talking about this, then look for what you have here. And same thing for here and here. So first thing, for conditional distribution, you are going inside the cell. So cell is always your numerator. Now, when you talk about the denominator is little tricky or little bit work in conditional distribution. In your marginal distribution, this is the denominator that we always take, right? In conditional distribution, we take this also, but this is not the only denominator. And let me make a better one. Let's use this one. So if we are talking about female who have almost no chance, and I'm talking about among the females. So if I'm looking for among the females, so first thing I'm going to the cell, female almost no chance, 96 females. Among the females, how many females are there? These many, right? So I'll divide with this. If somebody is interested in how females almost no chance among all the people who were surveyed, and how many were all? This many. So my denominator is this. My numerator remains the same. It's not changing, right? This is coming from the cell. But my denominator can be either this or this. Or if I'm looking for female, almost no chance, among all who has no chance. How many people have no chance when they surveyed? This many. So I can divide with this. So you can divide or you can take the denominator, either the respective sum column, the column sum or the row sum or the total or number of all the observation. So your denominator can be this, this, or this. And as I mentioned in your Stat 108 notes, there are some examples solved step by step. And once you are done with that example, there is another data set that are provided that you can solve by yourself to get an idea how to work with conditional distribution, how to work with marginal distribution. And once we are done with that, how do we graph them? Is pie chart an appropriate graphical representation of the categories percentages? When I add up, it's more than 100% or it's less than 100%, or is it the same? Is it 100%? Then I can do. And I think we did some example here last time. So, and again, I don't know if I mentioned or not, in the book, there is a summary of each chapter towards the end, right before the exercise. So it is kind of same. It talks about the main points of main concept checkpoints. So you can go over those from there or here. And here there are step-by-step examples solved. And once you do the example, let's say once you solve this and you get this part, can we represent this in a form of pie chart? Anyone? If I need to do a graphical representation of this, can I make a pie chart or bar graph or both?
No, not a pie chart.
Not a pie chart, because when you add all this adds up to more than 100%. But yes, you can always make a bar graph representing this, this, and this. And again, the order does not matter. You want to do this first, this first, this first. You can do it either way. And it is a 4-step process. And we say that solve. First, state your problem, what actually you are looking for. Then, what's your plan of action? Then, how do you solve? Show your result. And again, I think I mentioned earlier, in statistic, interpretation or conclusion is the most important part, where you have to do the inferences, where you have to explain what you have done from part 1 to part 3. And these, if I get this, what does this mean to me in terms of the context that is provided to me? So explain that in simple word using your question context. And that is, we are going to learn more in chapter 6 and 7. And there is a course, Stat 301, which is a writing intensive course, where in that course we are talking mostly about the inferences, about every single thing in the statistic. If you do this, how do you explain this in words? What are your results when you do hypothesis testing, p-value, mean, and all? And you will do some part of that in the project also. And here are the examples. So let me just quickly go over the last topic. And if I have time, then I'll come back to this one. So marginal, conditional. Any questions about marginal and conditional? Okay, if not, Simpson's paradox. This is an important application for, you can say, two-way tables. Once you know what a two-way table represents, what is your marginal and conditional distribution, then you can also check if there is a Simpson's paradox going on or not when you look at your results. And what that Simpson's paradox is, when you look at two individual two-way tables and you get some results, but when you combine those two-way tables, the results reverses the direction. So whatever your result from your first, or you can say individual two-way tables are, when you combine the table, the results are totally different. Or let's say if you have a combined data set and you look at a two-way table for their conditional distribution and get some result. And then you can see, okay, this data set is coming from two different places. And let me see if the same thing is happening there also. And then I look at two individual two-way tables coming from totally different places. And when I look at their results are totally opposite than what you see as a combined table. And that is called Simpson's paradox. And why we have this situation when we have two individual tables, we have the result. Combining should not be a problem, it should be the same. The problem is there is a lurking variable. And as we mentioned earlier, lurking and confounding variables. One is your hidden variable, one is your mixed variable. So if there is a hidden variable that is not in the picture, that is neither in X nor in Y, but that is still affecting your results. When we keep that lurking variable into consideration, and when we ignore that lurking variable, we get two different results. So keeping the lurking variable will give me some other results, but when I ignore it and I look at the combined data set and I said that, okay, it does not matter to me, then it will give me a different result. And let's look at an example for that. The definition for Simpson's paradox. When studying the relationship between two variables, there must exist a lurking variable. Again, lurking variable, and we also talk about confounding variable. And you can look at 2.7 also. But again, we mentioned confounding variables. Confounding variables are mixed variables where you can, on the response, you cannot see or you cannot differentiate if the result on the response variable are because of this or because of some other variable. So when you see a mixed effect on Y, that either from X or X1 or X2 or some other variable, then we talk about confounding variable. So I can see a mixed effect. But when we are talking about lurking variable is nowhere, but it is still affecting your results. And Simpson's paradox is basically talking about keeping the lurking variable or ignoring the lurking variable. Somebody had a question? Okay, I'll suggest you to mute yourself if you are not talking. All right. So an association or comparison that holds for all several groups can reverse direction when the data set are combined to form a single group. The reversal is called your Simpson's paradox. And again, with the words, it does not make sense until we see how it happens when we actually see the numbers. So let me go to the example, and it's the same example that you have in your slide that is solved here. So let's talk about this one here. And as I mentioned, there are a lot of examples here. You can work for marginal and conditional distribution. So let's look at this. It says that consider the acceptance rate of the following group of men and women who applied to college. And let's say that is UNCG, just for an example. We got the acceptance rate for male and female who applied for UNCG. And this is what we get in two-way table. So male, these many got accepted, female, these many, male, not, female does not. So if just looking at this data, just looking, not doing anything, can I say that more males are accepted than female, just looking at these two numbers?
No.
No, because 198 looks bigger than 88, but 198 plus 162 out of 360. So there are more mail applied, and that's why there is more acceptance rate. Here, 88 got accepted out of how many? There were only 200 comparatively to 360. So we cannot just compare these numbers. So that's why conditional distribution comes into play. Just looking at number, we can say, oh, 198 is more than 88. Why I need to work? I'm just done. No, the thing is percentages are more appropriate. So we need to calculate the percentage. What is the acceptance rate for mail? First, I need to see how many mail got accepted out of how many that have applied. And then I'll get that percentage. Similarly, I can see that many female got accepted out of that many. By the way, if you look at this table, first thing, you created an extra row, an extra column, because you need that, the total. And this is not given to us in the table. So we created, and then we can see 360 plus this 560. And I can add these two and I get the same. And if it is not same, that means there is some calculation work that I need to go back and check. So now I have a two-way table. I created the margin. The question is asking you who got higher acceptance percentage. So who got higher, male or female? First thing you need to, check. Check that. Once you check that, male and female, and then the next it's asking, is there evidence of discrimination? So first thing we need to check who get higher acceptance rate, and then we can talk about the second part. So higher acceptance rate, 198 divided by 360, I got this, and female this. And again, if I look at these numbers, I can say, oh, I can still see male acceptance rate is higher than female. But again, this will be not correct way to check. So the correct way is, how about you have, let's say, only 100 here and only 12 got not accepted. Still, you say that 88 is smaller than 198, so male has higher chances of accepting. So my idea is like, do not just go with this number. Look for how many accepted out of how many applied. If I look at only 100 applied, then I'll say 88 over 100. So 88% of female got accepted and they have higher chance than male, right? So just looking at the number is not a good idea. Again, we need to go inside the cell and then look for the sum total of that particular row or column depending upon what it is asking. So 198 got accepted. Out of this, you get this, same thing. Now the second question is, it's saying who got higher acceptance rate? We can say that male got higher acceptance rate. Now the question is asking, is there evidence of discrimination? We don't have any other information except only these two numbers. And if we are just looking at these two numbers and taking a decision on the basis of two, what do you think? Maybe if I look at these numbers, 55% is higher than 44% because I'm looking at the percentages. So this is one part of the problem where I looked at this and I say, okay, 55% is higher than 44. So maybe there are chances of discrimination against female, more male get accepted. But now I look at the other picture. This data is the male and female who applied to college. So this is the overall data. But this data is coming from two different schools. One is from business school, one is from art school. So let's look at the individual two-way tables. And when we combine those two-way tables, then we get this table. So here, excuse me, consider the acceptance rate when broken down by type of school. Who got higher acceptance percentage in each school, male and female? Again, the same question, and if there is discrimination going on or not, just on the basis of that, we'll see. So this is the data set that comes from business school. And this is that comes from art school. And if you look at this, when I add 18 plus 180, it gives me 198. 24 plus 64 gives me 88. So it is the combined table of these two. When I merge these two tables and just look at males and females or group of men and female applied, I got this table. But this big table or combined table comes from these two individual tables. If you look at 120 plus 240, this is 360. 120 plus 80, 200. And when you add this and this, it will add to 560. So I have these two-way tables, or you can say that I have this data set from two different schools, business school and art school. I combined the data set of these two, and this is my big picture. And this big picture says that more males are accepted. Now look at this one. How many males were accepted in business school? 18 out of 120, and the percentage is 15. And female is 24 out of 120, and it's 20%. Looking at these two results, I can say that female has higher acceptance rate, right? 20 is higher than 15. Same thing I'll do here. 180 got accepted out of 240, and then 64 got accepted out of 80. And you see 180 is bigger than 64. But when I look at the percentages, looking at this, 64 value is higher than that. So just looking at the number will not give us the values. We need to find the percentages. And when I look at these two tables from business school and art school, what I get in both cases, female has higher acceptance rate. So can I say that there is a discrimination against male going on? When it comes to the school, which school you are applying, more females get accepted, but overall more males get accepted. So again, from this result, from this discussion, we get the result that we cannot talk about the discrimination at this point, because here we are talking about two individual tables. And when we combine, we have different results. Individual tables have different results. So there is a application, or there is Simpson's paradox going on. And this Simpson's paradox is reversing my results. So what result I get here, female has higher acceptance rate. This result is totally opposite here, when here we are saying that male has higher acceptance rate. Using the same table, same numbers. And what are the lurking variable, or what is the lurking variable? Lurking variable is type of school. When we ignore what type of school or which school these people applied, then we have the result where male got accepted. And when we take the school into consideration, business school and art school, our results are totally opposite. And that is called Simpson's paradox. Again, Simpson's paradox, you need to understand the definition of Simpson's paradox. Sometimes a statement is given to you, and then you need to read that statement instead of just solving this. What does actually Simpson's paradox mean? So when you work with individual tables, or you can say that when you keep the lurking variable into consideration and when you ignore the lurking variable, the results totally reverse the direction. And that is your Simpson's paradox. So there might not be a question on Simpson's paradox where you have to solve this part and check. There may be, but there might be a question where the statements are given to you. You read the statement and see where is this application applicable, where the results are changing the direction when we are combining and when we are not combining or looking at individual with their lurking variable effects. So this is an example of Simpson's paradox. This is evidence of the effect of lurking variable. And here the lurking variable is type of school. You keep the lurking variable into consideration, then female got higher chance. And when you do not keep that, then male got higher chance. So technically there is no discrimination going on. And when in the court cases, a lot of our stat professors are doing consulting in court cases, and there you can see a lot of these things happening in real. Even a small things can change. And in later chapter, we will talk about hypothesis testing and how to set up your statement. And if you, I don't know how many of you get a chance to watch a court case, or maybe in your Netflix or somewhere, there are so many shows. So my whole point is like, statisticians play a very important role in those court cases because we need to see if this is a true statement or not. What can be in between? So here, if somebody say, "Oh, there is a truly discrimination going on between this and this, so more males are accepted or more female," and then we can see that there is not a big deal. Let me just do this test and check if there is a lurking variable that is playing. And similarly, small thing that looks bigger, but when you actually see him, it's like, oh, it does not look significant. The value is so down, and then you can check that part. All right, let me go back to the slides. And sorry, there is one more example here on Simpson's paradox. So if you get a chance, go do that one. You can look at the book, and you can look at your Launchpad extra resources. You'll find something more. So Simpson's paradox, this is the same example that we just discussed, 198, 162, and then 360, so 55%, 44%. So here it is just given you in the form of a table, but you saw the split. Where is it coming from? 198 divided with 360, that gives me 55%. And same thing, I get 44%. And then it's asking you the same. So in that example, it's solved manually, and then you can see step by step. But here, the steps are not given, just the whole values are given. Or you can say another table is given where you summarize all the results. But there, everything is solved. So that's why I want to go over with that. And same thing is done here, business school and art school. And then you can clearly compare. 15% is less than 20%, 75% is less than 80%. And it's also talking about the same thing, that when we are talking about Simpson's paradox, there is a lurking variable. When you keep, you ignore, you will see totally different results. The last one, the questions on the question of causation, explain association. So instead of going over all this, let me just talk about these concepts here. So when we say association, we have been talking about this from the beginning of this chapter. Association means any relation. And when that association is linear association, we call it correlation. Or you can see that this is the summary of what we have done so far. Association, it can be any relation, not necessary that it should be linear. When it takes the form of a line, then we call it correlation. Correlation is denoted by this or this symbol. We call it R, correlation coefficient, or you can call it as rho. Rho is a number between -1 and +1. The closer to 1 and -1, we can say strong correlation. Closer to 0, weak correlation. 0, no correlation. When you have linear association, or you can say that when you have correlation, then you can see that if that correlation is positive or negative. Once you know it's positive and negative, again, you can see how strong it is, either in positive or negative direction. If it's close to -1, it is very, very strong negative correlation, very, very strong positive correlation. And then here it says establishing causation and causation. So let me talk about this. When we are saying causation and correlation, they are two different things. When we are saying correlation, we are talking about linear relationship. When we are saying causation, we are talking about that there is a cause and effect relationship going on. So when we are saying correlation, we are saying there is a linear relationship going on. But does correlation implies causation? If there is a correlation, I can say there is a causation going on.
No.
No. Maybe, but I'm not sure. So let's say I have two variables, X and Y, and I use the same example that we used before, smoking and let's say lung cancer. And the data supports that. There have been some testing done in the past, or it's still going on. And that data supports that smoking causes us. Yeah. Sorry. Where are here? So there, and the data said that there is a linear relationship between smoking and lung cancer. And it says that positive linear relationship. So that means, let's say, and I'm not saying that very strong, but there is a positive linear relationship between smoking and lung cancer. So that means, on the basis of this, I'm saying that people who smoke have chances of or higher chances of getting lung cancer. That is from the data. But can I just say that if you smoke, you will get lung cancer for sure. And if you do not smoke, don't worry, you will not get any kind of cancer. Can I say that?
No.
No. So we see the data that we get that there are chances if smoking, or you can say that smoking with if you're smoking, you will get chances of getting lung cancer, and it is a positive linear relation with the data that we work with. But no matter how strong your correlation is, it does not imply causation. So correlation does not imply causation. We cannot say that whoever smoke, and I know that there is a correlation, so whoever smoke, you will get lung cancer for sure. No, we cannot say that. So correlation does not imply causation, no matter how strong correlation is. Cause and effect relationship is not just because of correlation. So this is one important application. Sometimes we see that, oh, there is a correlation going on and that correlation is positive. So yes, there is a cause and effect relationship going on. There may be some mixed variable. There may be some hidden variables. And again, when I'm saying smoking and lung cancer, not necessarily just because of smoking. I know a couple of people who never smoke in their life and they have that. And that can be from other things also, like maybe you get it through your parents, maybe you get it by birth when you were born, or maybe you get it because you have some other disease going on. So there is, when we are saying confounding variable, so when I'm talking about lung cancer, the effect is not just because of smoking. There are some other variables also that are playing a role in my Y or predicted value of Y, or in my response variable. So response variable, there are other, or you can say there are mixed variable, and I do not know this effect is just because of my explanatory variable or there are other variables. And yes, there are other variables, but in this particular case, I'm just taking my explanatory variable as smoking and looking at my response variable as lung cancer. So I'm just looking this linear relationship and examining my X and Y. But there are other variables that are mixed, or they are there, that are affecting your response variable. So this is not just your explanatory variable. So sometimes there are confounding variables. Sometimes there are lurking variables. They are not even in the picture, but they are affecting your results. So again, this is an important application that you need to know, that correlation does not imply causation, no matter how strong or perfect correlation is. Even though if you have this positive one or negative one, still we cannot say that there is causation going on. So cause and effect is a different thing, and we will talk about that in a later chapter also. But this is about correlation. Once you know there is a correlation, R, you have the value of R. This value of R is called the coefficient of correlation coefficient. Once you know there is a correlation going on, you try to fit a line inside those points in such a way that these points are as close as to your line. And when you fit a line, to see if this is a good fit, we use residuals or residual plot. And again, these residual plots are hard to make manually. So we use software to make those residual plots. And when you get a residual plot for a linear relation, again, you get residual plots only for linear relationship because you see correlation and you try to fit a line here. And then so you look at this, and if all these points are scattered around 0, that means it is a good fit. But you will still see if there are outliers in your data set, let's say here and here, the line is something like, so you can still see the outliers in that. And when we talk about residual plot, we make +2, -2 bound to see there are still 95% of the observation in this bound. And then if there are something outside, there 5% of the observation can lie outside. And again, there's a whole topic to talk about for residual plots. But in this course, we are not going in detail. As long as you know that why do we make residual plots to see how good fit our line is. And when we are talking about residuals, what actually the residual is, when you try to fit a line, you have an observed point. That is the point that you have in your scatter plot. But now when you try to fit a line, where is this point lying on your line? So this point is here now, and this is my residual. And we will have residual for each of these points. How many points you have in scatter plot, and then you use those residuals to draw the residual plot and see if they are all close to 0. And again, definitely if they are below the line, above the line, same thing you can see here also. And you will see the 0 in the middle and scatter around 0. And then you will plot these residuals. And residual, this is your observed value that is given to you in the scatter plot. And this is your predicted value. And residual is the difference between your observed and predicted value. So that is residual. Once you make your residual plot, you see the best fit line, and then you use something called R-square or R-square, and you get some value. Sometimes this value, again, when we are talking about R-square, you will have values in decimals as well as in percentage. And you have done your homework 2.2, 2.4, where the values of R-square are given to you in your Minitab or SAS or SPSS output, and you need to convert that into percentages. And there is a question in your homework assignment, which I saw that a couple of you missed, where the value of R-square is given to you something like this. I don't know the exact number, but I see something like this. So if you have something like this and it's asking you what is the value of R, 0, 1, and there are other options. So when you see this here, you say that, oh, it is not 0 for sure because it's 0.4. And then it's not 1 either because it's in between 0 and 1. And then you look for other options. But look at this part. This result is coming from a software. So instead of writing everything in the decimal, it's given to you in this form. And I think you must have learned that somewhere in middle school. E to the -5, the calculator does not provide us this value. So it is 10 to the power -5. So that means this value is 4.356, 10 to the power -5. That means you are dividing this, and whatever that number is, you can check. 1, 2, 3, 4, 5. And when you divide with this, your decimal move 1, 2, 3, 4, 5. And your decimal will be here. 1. So when your decimal move, and now you look at this is the value of R-square. You take a square root of that, then you get the value of R. Because the question is asking you, what is the value of R? And when you look at that, this is very, very close to 0. So 0 is the right answer. But just looking at this number, it does not feel like, oh, 0, no, 0 there cannot be. So R-square is also called as coefficient of variation or variations in Y because of X, variations explained in Y using the explanatory variable X, or coefficient of determination. So we can, if we know R, we can find R square. If we know R square, we can find R. Again, we need to see plus and minus. And then there are questions in your homework assignment where the value of R square is given. And the question is asking, is there a negative correlation? Is there a positive correlation? Then again, R square will not tell me positive or negative. So go back to your output and look at the slope. If the slope is negative, or if you have a scatter plot, if it is negative, then value of R is negative, otherwise it's positive. So that ends your chapter 2. And if you guys have any questions, let me know. And if you want me to extend your homework assignment by another day, then let me know that as well. And I guess that's all for today. Happy Friday again, and have a nice weekend. I'll see you guys on Monday. Thank you.